This is the UE-1, my homebrew 1-bit vacuum tube computer that I've been building from the ground up for about 3 years now. And it's complete. And it's also broken. It doesn't work right. In the previous episode, we punched out this program right here, which should calculate the Fibonacci sequence up to 21 and display the result on the output register down here. But instead of displaying 21, it displays 0. So this program doesn't work at all. But it is a good program. I went through and verified it byte by byte, and we can run this program in the Quick Basic emulator, and it works exactly like it should. So something on the actual hardware is not working correctly. However, this program is a memory test program. It fills every single bit of the scratch register, every single bit of the output register, and then empties them out. And this program works just fine. So what gives? What's going on? What's different between that program and this program? Well, I think we might actually have a speed issue going on here. But just slowing down the tape doesn't actually solve the speed issue, because the speed issue is going on somewhere deeper. I think it's more like a setup and stabilize thing. I don't really know. It's a pretty confusing system, so let's sit down, try to figure out what's going on, and maybe we can get this thing running Fibonacci by the end of the day. Just to be clear up front, I don't actually know what's wrong with the UE-1. I have a feeling that it has to do with speed and potentially the clock or how we're generating the clock. But in order to understand why I have that feeling, we need to kind of take a look at what the UE-1 is and some of the questionable design decisions that I made along the way. And initially, I wanted to build a replica of the SAP1, which stands for Simple as Possible 1. And this is an 8-bit design that was made quite famous by Ben Eater, as he built it up on breadboards using 7400 series logic. And if you haven't seen this series, go watch it immediately. It's just some of the greatest YouTube content that's ever been made. And it was a massive inspiration. When I came across it, it lit the fire in me that sent me down this life path that I am absolutely loving. So Ben, I don't know if you watch any of these videos, but if you do, thank you so much for everything you do, man. Just absolutely stunning work. But also the SAP1 would have been impossible for me to build out of vacuum tubes, particularly as my first ever homebrew computer. I didn't really know what I was doing at the beginning of this project, but I did know that the SAP1 was biting off more than I could chew. So I started looking at different designs, and ultimately I settled on a design by Motorola for the chip, the MC14500. This is a 1-bit industrial control unit that looked like it was something I could tackle. And I think it's a lovely design, but there's a lot of shortcomings with it. And if I were to do it all over again, I would not choose the Motorola chip. I would actually choose the TI TMS 1000. I think this is a really graceful 4-bit design, and it was used in like pretty much every calculator that TI made, as well as like really notable toys like the Speak and Spell and Simon and all these other things. And so if I were to do it all again, I would have gone with that one. But for UE2, we're not even gonna do that because I think we have actually a better design. But in order to get to UE2, we gotta get UE1 fixed. So UE1 is the Motorola MC14500 minimal ICU system. And you can see we actually have a bit of a layout of it right here. And it's a really simple design. We have the CPU that uses a 4-bit instruction, and then we have a 4-bit memory address. Now we combine this 4-bit memory address with a write signal, which is coming from the CPU, to allow us to address either 8 bits of RAM, the result register on loopback, 7 bits of external input, or 8 bits of external output. Now, since we only have an 8-bit instruction word, 4 bits for the instruction, 4 bits for the memory address, we're actually executing code directly from the paper tape. So as those 8 bits go across the photodiodes, they stabilize, and then the tractor feed hole in the center of the tape is much smaller, and we're using that for our clock. So it's 1 instruction per clock cycle, which is quite nice. It makes programming it quite simple, but it means that that single clock cycle has to do a lot of work. So I actually set up the clock in such a way that we have a bit of an RC delay. So we have 2 rising edges and 1 falling edge. The first rising edge is where we latch in the instruction. The second rising edge is where we actually execute this instruction. And then the third falling edge is where we latch the result register or the carry register. So having the three phases of the clock set up like this is instrumental, and it was the only way that it was going to happen. But the way that I did it was with an RC delay, and I think I might have made that RC delay a little short. So I think what we're gonna do today is we're gonna pull the scope out, we're gonna plug it in, and then maybe shift that delay further out to hopefully give the instruction and the data bus time to stabilize before we actually execute that instruction. And because of the way I built the logic on this thing, clock 1 is active low and clock 2 is active high. If we look at the schematic here, we can see that clock 2 on the bottom here has an extra inverter to make sure that it's essentially the opposite of clock 1. But on the bottom half here, if we look, we've got this 220K 22 nanofarad RC delay going on, and then it goes into 2 inverters before it hits 2 buffers to go all the way out. So that's our RC delay, and that's our extra inverter to get it going. And I've got the 2 scope probes set up here. Yellow trace is going to be clock 1, green trace is going to be clock 2. And looking at the scope here, we can see that clock 1 is sitting high at about 18-19 volts. Clock 2 is sitting low at about 3 volts. Clock 1's a little lower than I would like, but I think that's going to be fine. So let's go ahead and run a program through, and we should be able to see these 2 clocks toggling. Yeah, we can see the 2 clocks toggling right there. All right, so let's zoom out just a little bit more here, and we'll get a single shot of that. Excellent, and we can see our clock pulse is actually quite skinny. So if we zoom straight in on it, there we go. This is at 1 millisecond per division, and we can see that the yellow trace, which is clock 1, is about 1, 2, 3 milliseconds long. And then our delay from clock 1 to clock 2 is really, really tight here. Boy, yeah, if we zoom in far enough here, we're down to 100 microseconds per division. So it's about, I don't know, I'd say 100, 200, maybe just a touch over 200 microseconds. That delay right there might be too tight. Fortunately, when I built this thing, I had an inkling that the capacitor value that I chose would be wrong, so I put that capacitor in a socket, which is right here. So if I just reach in there and I grab that, I can pull that capacitor out. It's a 103, so let's toss a 104 in there. This is a different type of capacitor, but it shouldn't make much of a difference. That should slow it down. 104 is a lot larger, so it may actually slow it down too much. Back here on the scope again, we'll do another single shot, run it through. And that actually looks potentially a lot better. We can see that the delay now is quite significant, and it's landing right in the middle. But, well, it made absolutely zero difference. We just get one little blip and then absolutely nothing else. But just to make sure, let's run the memory test program here. So I'm going to go ahead and load this thing up, and then we'll go ahead and run this through, and we should see the output register filling and emptying here. Yeah, that still works totally fine. So I had a hunch, but it was wrong. It was not the right hunch. We'll keep working at it. I think it's time to leverage a bit of the power of the scope here. And I think what we can do is we can get a scope shot of the entire program running and then zoom all the way into individual clock pulses and still have enough fidelity to see what's going on. So I made a list of every instruction of the entire Fibonacci program and what the value of the result register, carry register, data bus, scratch register, and output register should be for each instruction. So I've got a bunch of probes set up here, but really we're only going to be looking at 3 signals. The 4th signal is going to be the input enable register signal, and I'm using that to start my capture. We'll set the scope to single shot, and then I'll go ahead and hit start over here. And yeah, there's our whole program. Now I just need to sit down and analyze this. Fortunately, the speeds we're working with here are genuinely slow, which means the scope should be able to grab enough fidelity to really see what's going on. And as we zoom in here, yeah, we can clearly see what signals are doing what. So Let's break down this shot because there's a lot going on here that is really fascinating. First, clock 1 is in yellow, and remember, it's active low. It's decently clean looking and is an excellent frame of reference. The data bus is in red, and we can see it wibble wobbling outside of the clock pulse. What's happening here is the memory address is stabilizing in between clock pulses. Particularly on the right side of the trace, you can see the data bus go low and high again. The point at which it goes low is the space in between holes on the paper tape. So it selects a memory address of 0000 at that point, which is the scratch register, and that is currently storing a 0. But where it goes high is where the holes on the paper tape stabilize, and it selects a memory address of 1000, which is the results register looped back, and that is currently storing a 1, which we can confirm by looking at the blue trace. That is the value of the results register, and we can see that it is indeed a 1. Finally, the green trace. This is the IEN, or input enable register. We can see it goes from 0 to 1 right in the middle of the clock. This is where the rising edge of clock 2 hits, latching RR into the input enable register. This is also our trigger point, and since this happens at instruction number 1, it's a good place to start counting instructions from. And now that we know what we're looking at, the tedious part starts. I just need to sit down and scroll through the entire program, clock pulse by clock pulse, looking at the value of the results register and data bus, and comparing them against my notes. It's kind of like looking at a logic analyzer trace, except I can see a whole lot more fidelity in where traces are transitioning at, as well as how low and high they actually get. Plus, my logic high is around plus 20 volts, which would upset most logic analyzers. But you can see that as I scroll through on the scope here, we can clearly see the data bus stabilize before the clock. Although in this particular shot, I'm in the middle of a long stretch of nothing exciting happening. But this has been incredibly enlightening because something has indeed jumped out at me. Enough that I think I need to pull some boards, notably the right signal generation board and the connection board that feeds a clock to that right generation board. Well, I've discovered a problem. I don't think it's the problem, but it's certainly a problem. I was following through the steps here, and there were things that were jumping out pretty early on, but most instructions were executing pretty much on point until we got to instruction 44, and then everything went kind of sideways. But the stuff that was jumping out to me, I decided to look into that first, and that's shown on this scope shot right here. The yellow trace is the clock and it's active low. The green trace is our IEN signal. We just use this for trigger, so that can be ignored. The blue trace is the result register and the red trace is data. And we can see that the data bus value is changing with the falling edge of the clock. And if we remember back to my little diagram here that shows how the clocks are laid out, the falling edge of clock 1 should only be latching the 4-bit opcode into the instruction register and doing nothing else. The opcode should be executed or a value should be stored into memory at the rising edge of clock 2. So why is our data bus value changing on the falling edge of the clock? And that's because actually we're storing the value into memory on the falling edge of the clock by accident. So this is how the right signal is generated. And we can see that the collection of 6 NOR gates here is just the output enable register, and the output of that feeds into a NAND gate that is then sent out to create the right signal. And then we have a little OR gate down here for whenever we do a store or store complement instruction. And then the final input to that NAND gate is clock 1, and it should be clock 2. Not only that, it doesn't need to be inverted because clock 1 is active low, but clock 2 is active high. So actually on this little board right here, this is the right signal generation board. This inverter should not be being used at all. And this board here, which ultimately supplies the clock 1 signal to it, is miswired, and I need to change that to be supplying the clock 2 signal to this. So I've got some bodges to make, then we'll get these back in there and see how behavior changes. I need to change a jumper setting, which will require removing a bit of solder. Fortunately, single-sided PCBs without a solder mask are easy to desolder with just a bit of solder wick. It seems that I knew this clock 1 versus clock 2 thing would be an issue, and I provided a little jumper change to select between the two. I just got to move it up a notch, and now clock 2 is being sent to the right generation board. However, I didn't provide an easy way to bypass the inverter on the right generation board. For that, I'm going to have to do a bit more desoldering, and then remove a jumper and a 220k ohm resistor. Then I'll carefully bend up a new long jumper and get it in place. Effectively, all I'm doing here is taking the input to the inverter and jumping it over to the output from the inverter. But by removing that initial jumper, I also disconnect that inverter from the output. It means I have a tube on here doing absolutely nothing now, but it's better than recutting the entire board. All right, she's all back together. I don't necessarily think that was the problem, but it definitely was a problem. So I am expecting behavior to change somewhat. So I've just powered it on. I let it warm up for about 3-4 minutes here. So I'll go ahead and push the button here. We should see some blinking down here. Or, you know, nothing could happen. All right, I was doing a bit of testing because it didn't really seem to be working right, and I ended up going back to the original delay capacitor on our clock over there, and then I just ran it again to get another scope shot. I looked over, and that's the correct answer, 10101. I didn't see it happen. I just noticed that it's sitting at the right answer. I don't know if it just stumbled onto it through chaos or if it actually calculated the right answer. And I haven't tried running it again, but we'll push the button one more time here. And that time it didn't get it. Oh, so close, so close. That time it got it. I could see it count up. That's 10101. I don't think it's consistent. We'll give it another shot. I bet you it fails this time. Yeah, total chaos that time. We'll go one more time here. And that time it was perfect. This is wild. It seems to work correctly for one loop, then fail on the next loop, then work on the next loop. So if I hit it again, chaos. Does not work. We'll do it one more time. That time it worked. I have no idea why, but it's consistent. It's consistently giving the correct answer. Probably there's an error in my program or some way. I don't know. But that's 21. That's 21. 10101. That did it. That did it. It's been years in the making, but if I push this button, it gives the wrong answer. And then if I push this button again, it gives the right answer. It just calculated Fibonacci. We've got 21 on the output register. That is the correct number. I don't know why it works every other iteration. There's something in the reset whenever we loop around that's not getting reset correctly. But hey, that's 21. This thing just did complex math. How epic is that? The UE-1 actually legitimately works. Oh, that is so cool. Now there's a lot of fine tuning that I probably need to do. I need to figure out why the loop doesn't work. Shouldn't be a program issue, might be, I don't know. Also, the bell still doesn't work, so I still gotta try and get the bell functioning correctly. But everything else seems to be working perfectly. Our memory is doing exactly what it's supposed to do because that Fibonacci program hits every single bit. Just absolutely stunning. I am so happy. So I want to thank you all so much for watching, and I hope to see you in the next episode.